This is a video for MEI Core Pure Mathematics, Vectors 4, Lines and Planes, 4.1, the intersection of a line and a plane. A brief recap about equations of a plane in 3 dimensions in vector form. If we've got a plane, as I've got here, with a normal vector n, and I know the position of a point on the plane and want the position of any other point on the plane, then I can use this equation, r minus a dot n equals naught. That rearranges to give me r dot n is equal to a dot n. Now remember, a is going to be a constant, and obviously the normal vector will be a constant, so this bit here is really just d, some value. And if I think about r as being x, y, z, and n as being n1, n2, n3, then I think you can see that this bit, using those forms, becomes this thing down here. So the Cartesian form is n1x plus n2y plus n3z. You could have equals d or plus d equals naught. The sign is immaterial because d is just a constant. If we've got a line and a plane, one of 3 things could happen. Either the line could intersect the plane at a single point, like it does here, or we could have, plane its normal vector, we could have the line being parallel to the plane, and in which case it would still be at right angles to the normal vector, but it would not lie within the plane. Or we could have it lying in the plane, and in which case it would be like that, still at right angles, but it would then have at least one point. Indeed, it would have all its points in common with the plane. So in these 3 situations, you get one single point, no points, or all points being in common. Let's have a look at this example. We want to find the point of intersection of the plane pi and the line L, and here they are given to us in Cartesian form and in vector form for the line. And a sketch is always helpful to see what's going on, to just try and picture in your mind what's happening. And here's my line. I'm assuming that it looks something like that, and it intersects the plane at a particular point P. Now, we've got a little hint here. How else could we write R? Well, you've got R here in terms of the vector form, but remember from the previous slide we also said that R is x, y, z, and that means that we can pull out from here values for x, for y, and for z, which I can then substitute back into here, and that's exactly what we're going to do. So starting from here then, we can say that x is equal to 2 minus s, y is equal to minus 3 plus 2s, and z is equal to 4 minus 3s. So if this is any point on the line, if I plug it into here, I should be able to find a value of s, if there is one, that satisfies this equation. So plugging that into the equation for pi, I'm going to get 2 lots of 2 minus s, minus 3 lots of minus 3 plus 2s, plus 4 minus 3s, so that's my x, y, and z, must be equal to 6. That gives me 4 minus 2s, plus 9 minus 6s, plus 4 minus 3s is equal to 6. And then collecting these together, I've got 17 minus 11s is equal to 6, and that gives me s is equal to 1. And so my point of intersection is on the line when s equals 1. So I've got 2 minus 3, 4, plus minus 1, 2, minus 3, and that gives me 1, minus 1, 1, So the point P is 1, minus 1, 1. And there's that written up a little bit more neatly. This is extracting the components x, y, and z from the equation for the line. That's the substitution into the equation for pi. Tidy it up, and we get through to s equals 1. So that's the parameter value in this line for the point of intersection. Plug that in, and we end up with p is 1, minus 1, 1. The next and final video in the sequence is 4.2, the angle between a line and a plane.